Hi folks. This lecture is all about looking at the trends in the neutral atoms of matter and using the periodic table to predict those properties. Many of these trends are a review, so we won't have to spend too much time on them, but it's nice to have them all in one location.
Shown here is the periodic table with the electron configurations of each of the elements placed under the symbol. The configurations for reasons of space are just of the valence electrons. Now we already know how to find the core of the configuration, the noble gas. Now just to make sure we have this right, let's do an example. Now for the element iron, Fe, the full electronic configuration should be argon in brackets 3d6 4s2, but we have left the argon part off the table. Now the red configurations denote elements with ground state electronic configurations that are exceptions to the normal buildup rules. Now we'll refer to this table and our regular periodic table often to justify the properties and patterns we see in the elements in the next few slides. So keep both tables ready as we discuss these trends. Again, this should be a review, but review never hurts. Now, what makes an element an element? Well, the answer is the number of protons, which are the atomic numbers in the left corner of each element on the table. Now, what determines the mass of an element? Well, most of the mass is in the nucleus, so the number of protons and the number of neutrons will determine most of the mass of an atom. The relative atomic mass found under the symbol of each element in the periodic table gives us some idea of the actual mass of the atom. Now, the general mass trend is obvious. Mass increases with increasing atomic number. Now, there are exceptions, such as the pair of elements argon and potassium, or the pair of elements cobalt and nickel, which we talked about in an earlier lecture, and a few others are on the table as well. Now, as we discovered, these exceptions are present because of the varying isotopic ratios and abundances, factors which can produce lower or higher atomic mass ratios than would be expected. What determines the groups in the periodic table? Well, looking at the electron configurations, we see that all the elements in a group have similar electronic configurations and the same number of valence electrons in the outermost orbits. The filling of the d and f orbitals, which we get into when we get into the d block elements, adds substantial numbers of valence electrons into the outer shell and complicates things just a bit. Now, how about the size of neutral atoms? Well, the size of the atom depends on the outer electrons placed in the probability density of the outermost atomic orbital. Now, shown in this table are the radii of the atoms. The sizes are in picometers, or 10 to the minus 12th meters. Now, the obvious trend is that as you go down a group, the atomic radii increases. Looking at the electron configuration, the principal quantum number of the valence electrons increases as you go down the group. And that quantum number, remember, determines the scope and size of the probability distribution. The larger the principal quantum number, the further out from the nucleus the distribution will reach. Plus, you're beginning to add more and more electrons into the core, which shields the outer electrons from seeing the full charge of the positive nucleus, and in effect, the outer electrons are feeling less positive charge from the nucleus, thus expanding the outer probability shell for these electrons. Now, as you go from left to right along a period, the radii of the atoms decreases. Now, this one can be a bit counterintuitive. Now, as we go and add an electron to the atoms in the row, we're adding an electron into the same principal quantum shell as the valence electrons of the previous atom. We aren't increasing any shielding effects of the nucleus, since these are not core electrons placed in lower quantum shells, but electrons placed in outer shells. Plus, at the same time as we're putting another electron into these orbits, we're also placing a full proton into the nucleus, increasing its attractive force for these outer valence electrons. The result? a shrinking of the probability density of the outer orbits, and a smaller atomic radius of the atom. Now here's a periodic table which has ionization energies for each atom in energy units of electron volts. An electron volt is a unit of energy equal to 1.602 times 10 to the minus 19th joules. The ionization energy in the table is the amount of energy it takes to knock one electron off the neutral atom. So the more bound the electron is to the atom, the more energy it'll take to knock it out. The ionization energy tends to decrease as we go down a group. The outermost electron, as we go down the column, gets further and further away from the nucleus, making it easier and easier to knock that electron off the atom. And just as in the case of atomic radii, as we're adding more and more electrons into the core, we're increasing the shielding of the outer electrons from the full charge of the positive nucleus. Now, as we move from left to the right across the period, the ionization energies increase. The reason is identical to that given for the decreased radii we saw when we went left to right in the row. The outer electron becomes ever more bound to the more positive nucleus because the added electrons are not shielding the ever-increasing positive charge of the nucleus, making it harder and harder to knock the electron off the atom. Now, if you look close at this table, you're going to find many exceptions to the general rules for ionization energy. There are a variety of reasons for the exceptions that are related to things like electronic configuration, electron pairing, shielding, and other electronic properties. These are interesting cases and worth investigating. So go ahead and look them up, but we won't get into these particular exceptions in this lecture series. Here you're going to find a periodic table with electronegativity values for the atoms. The electronegativity scale was established by the great scientist Linus Pauling to measure an atom's ability to attract electrons. In effect, the value reflects the atom's love for electrons. It makes sense that the electronegativities will obey similar driving forces as the ionization energies. For ionization energies, the stronger the electrons are bound to the nucleus, the harder they are to knock out. This pull by the nucleus will be equivalent to the atom's love for additional electrons. Pauling liked to think of fluorine having the standard top grade, a wonderful 4.0 EPA, electronegativity point average. Now, the other values on the table are relative to this 4-point scale. The electronegativities decrease as we go down a group, and as we move from left to right across the period, the electronegativities increase. This electronegativity increase follows the ionization energy trends as expected. So look at that slide for the justification of the trends. And also, just as there were many exceptions to the rules for ionization energies, you're going to find plenty here in the electronegativities as well. Again, investigate them, but we won't concern ourselves about these interesting cases in these lectures. The ionization energy and electronegativity trends guide our discussions about ions. We again show the common ions that we need to be most familiar with on this table. Knowing the electronic configurations and the idea that all the atoms want to be noble, it's easy for us to rationalize the charge on the atoms. Atoms tend to want electron configurations like the noble gas atoms, especially the alkali metals, alkaline earth, and the halogens. Alkali and alkaline earth metals only need to shed their valence electrons to be noble, becoming cations, and they only have one or two outer electrons to deal with respectively. Now, the electronegativities and ionization energies are low for these atoms, which also highlight their willingness to let go of these outer electrons. Halogens and other main group elements in the p block only need to gain electrons to have the noble gas configurations, thus becoming anions. Here, the electronegativities and ionization energies are high, highlighting the strength of the nuclear attraction for electrons. As mentioned before, things get a bit trickier with the transition metals, which have a lot more flexibility on how they might arrange the remaining valence electrons in the ion, so they can have more ionic choices. Let's look at the reactivity centers of the periodic table. The closer we get to the corners of the periodic table, the more reactive the elements become. For the metals on the left side, the atoms want to get rid of their valence electrons to become noble. And as we go down the group, the ionization energy and electronegativity values plummet because of the large principal quantum numbers of the valence electrons, denoting higher energies and larger distances from the nucleus, thus negating the attractive positive force the outer electron might feel. That outer electron for cesium, Cs, the element in the bottom left corner of the table, is just too easy to rip off. So cesium is a very reactive and unstable atom. Now the opposite thing is happening on the top right side around fluorine. The principal quantum numbers are small, denoting large ionization energies and electronegativity values. These atoms just need one or more electrons to become noble, and they have plenty of muscle to draw extra electrons due to the stout attractive forces felt on the outer electrons by a strong nuclear charge. Now just imagine what would happen if cesium and fluorine saw each other. Oh, there I've done it. I've gone and blown up another perfectly good lecture and lab. Anyway, you can see we have huge predictive powers and plenty of properties to determine how atomic matter might behave when they get around other atoms. I think we're more than ready now to begin our study of compounds, don't you? Excellent. I'll see you soon.